Welcome back. Lecture 20.2, where we're going to talk about the third law and how that relates to the unattainability of t equals 0. All right, you'll notice often that when I write these things in lecture, I don't write t equals 0, I write t approaches 0. So this is really the way we should think about it, is as we get closer and closer to 0. That's when we get these divergences, for example, in the heat capacity and the entropy. But we don't ever get to t equals 0. So we've already seen one way, but we'll talk about that again. But just as a starting point, as a reminder, so this is section 11.5 in Fin, and it's chapter 12 in Rex. So the point that this is about is that the third law is inconsistent with approaching absolute zero. So let's look at why. So we've said that the entropy must go to 0 as t goes to 0. And that's one way to state what the third law is, right? So if we have some curve of state 1, we have some other curve, say state 2. Let's say these are liquid and gas, or two different crystal structures, or two different forms of magnetism. There's lots of ways we can do work to think of running an engine as a refrigerator, right? If you remember in our Carnot cycle, the efficiency of our refrigerator was the heat we extracted from the cold side over the work. So there's lots of ways we can input work to extract heat. So let's imagine that we have two states. We know that the third law says, that S goes to 0 as t goes to 0. That means that there's no way to go from, say, state 1 to state 2 in any finite number of steps. So no matter what I do, you can see, because they're both going towards 0, it would actually take me an infinite number of steps, right? To get to t equals 0 would take infinite number of processes, right? And we obviously don't have infinities on our hands, so we can't actually get to t equals 0. This is kind of like this Zeno's paradox of the caterpillar jumping, not a caterpillar, a cricket jumping halfway to the wall, right? So if I jump halfway to the wall, and then halfway again, and then halfway again, and then halfway again, and halfway again, I never actually get to the wall. So the cricket should reach its arm out and touch the wall. But anyway, this is no cricket. So if for example, remember, so if S as a function of temperature did not have to go to 0, right? So this is not what happens but just imagine that if I had state 1 and state 2, where S was finite as t goes to 0, then I could do some procedures where, let's see, where I could move to T equals 0, right? If I was allowed to have some finite entropy at T equals 0. This is not what happens. So this is instead what happens. Okay, so I'm fine with that. This is consistent with the fact that we can't get to T equals 0. I actually think a more stringent definition, the book doesn't, is the second law. And that is that if I remember back to my refrigerator, my Carnot refrigerator, and I would write, oh, if it's Carnot, it can be, I can rewrite these as T's, and this is TH minus TC. And so as TC, the cold side goes to 0, my refrigerator's efficiency goes to 0. So I think this is even more stringent because even if I could have this, right, I wouldn't actually be able to do it because I could never build a refrigerator that could actually have enough efficiency to get out all of that entropy as T goes to 0. Okay, so that's all I wanted to say about the third law. That's the end of chapter 11. And I want to go on, and we're going to now talk about, in 20.3, the central theorem, or central equation of thermodynamics.